Today, we're diving into a story about a scientific earthquake, a moment that literally cracked our entire understanding of reality wide open. We're going to see how a single discovery shattered an idea that had stood firm for thousands of years. For as long as people had seriously thought about what the world was made of, one idea stood above all others: the atom. The name itself, from the Greek atomos, literally means uncuttable. It was supposed to be the final stop, right? The fundamental pixel of the universe. But in the quiet labs of the late 1800s, a strange glow in a glass tube started hinting at something, well, something impossible. All right, so to really grasp just how radical the discovery of the electron was, you have to appreciate the sheer weight of history it was up against. This wasn't just some new theory, this was an attack on a 2,000-year-old pillar of human thought. I mean, this idea of an indivisible atom had some serious history. It all started way back with the ancient Greek philosopher Democritus. He imagined the universe as just tiny, unbreakable particles bouncing around in empty space. It was a brilliant idea, but it was just philosophy. It wasn't until much later in the 18th and 19th centuries that scientists like Lomonosov and, most importantly, John Dalton turned it into real, hard science. This is John Dalton. He's really the guy who put the atom on a solid scientific footing. His atomic theory was incredible. It explained chemical reactions perfectly. He imagined atoms as these tiny, solid, indestructible little spheres. Each element had its own unique kind of atom with its own special weight. And for the chemists of the 19th century, this model worked like a charm. The atom was it. The bottom floor. End of story. Or so they thought. So let's get to the mystery that started to unravel all of this. While chemists were perfectly happy with their solid billiard ball atoms, physicists were off in their labs playing with a new toy, the vacuum tube. And inside it, they were seeing something that just didn't make any sense. So try to picture this. You take a glass tube, you pump almost all of the air out, and then you blast a high voltage current through it. All of a sudden, this strange, eerie glow appears, and it seems to be streaming from the negative plate, the cathode. They called them cathode rays. But what were they? Nobody had a clue. And this puzzle kicked off one of the biggest arguments in physics at the time. The scientific community basically split right down the middle, and pretty much along national lines. You had the German physicists who were convinced these rays had to be some kind of wave, maybe like light but invisible, moving through this stuff called the ether that everyone thought filled space. Then you had the British physicists who argued, no, these are particles, a stream of actual stuff carrying a negative charge. Both sides had good arguments, but neither could land a knockout punch. And this is where our protagonist enters the scene, a physicist at Cambridge University's famous Cavendish laboratory, a man named J.J. Thomson. He decided he was going to settle this debate once and for all. He was going to design an experiment not just to look at these rays, but to interrogate them, to force them to give up their secrets. This was the device that would change physics forever. Now, I know it looks a little complicated, but the absolute genius of it was in two key additions: a set of electric plates right here and a pair of magnetic coils. For the very first time, a scientist couldn't just see the rays. They could precisely steer and measure their path using forces they could control. He was basically putting the beam on trial. So here's how the interrogation went. First, with nothing on, the beam flies straight. Simple enough. Then Thomson switches on the electric field, and zap, the beam bends up towards the positive plate. That's Exhibit A. Whatever these rays are, they're negatively charged. But here's the brilliant part. He then turns on a magnetic field that pushes the beam in the opposite direction. By tweaking the strength of that magnet, he could perfectly cancel out the electric force, making the beam fly straight again. And in that perfect balance, that's where the secret was hiding. Having this kind of precise control was the key. Thomson knew he had stumbled upon something totally new, something elemental. And you can just feel his sense of awe in his own words. It's like he had captured some new kind of creature, one he had managed to tame, but he still didn't quite know what it was. The next step was to measure it, to give this creature an identity. Because he knew the exact strength of the electric and magnetic forces needed to balance that beam, he could calculate a really important property, the ratio of the particle's charge to its mass. This number would be its fingerprint. And when he crunched the numbers, the answer that came back wasn't just interesting. It was world-changing. It was something no one was prepared for. The charge-to-mass ratio he measured was huge.
way, way bigger than for any atom or ion they knew of. And there was really only one way to explain it. The particle's mass had to be impossibly, unbelievably small. How small? Around 1,800 times less massive than a single hydrogen atom, which, up until then, was the lightest thing anyone thought existed. This wasn't just some new kind of atom. This was a piece of an atom.
And just like that, the 2,000-year-old idea of the indivisible atom was gone, obliterated. The atom wasn't a solid little billiard ball after all. It had parts. It contained an entire inner universe, and science was about to take its very first look inside. Thomson stood before the Royal Institution in London and made his historic announcement. He called his new tiny particles corpuscles, a name that, didn't really stick. The name electron, which had actually been suggested a few years earlier, is the one we use today. But whatever you called it, the message was loud and clear. Science had just found the first piece of matter smaller than the atom. So, if atoms weren't solid little balls anymore, what did they look like? Thomson put forward the very first model. He pictured the atom as a kind of sphere of fuzzy positive charge, with his tiny negative electrons dotted throughout it. Think of it like raisins or plums stuck in a pudding. Now, this plum pudding model wouldn't last long, but it was a crucial first step into this brand new reality. It is almost impossible to overstate the consequences of this discovery. It directly led one of his own students, Ernest Rutherford, to find the atomic nucleus. It laid the foundation for the beautifully bizarre world of quantum mechanics. And maybe most importantly for us, learning how to understand and control this one tiny particle is the basis for, everything we call modern technology. The computer or smartphone you're watching this on right now, the internet that brought it to you, all of it works because we dared to shatter the atom and found the electron inside. What Thomson's discovery really proved was that what we think is fundamental today might just be a doorway to an even deeper, more complex reality tomorrow. The atom wasn't the final frontier. The electron wasn't the final frontier. Which leaves us with this incredible question. As we keep peering deeper and deeper into the fabric of our universe, will we ever actually find a true, final, indivisible particle? Or is it layers all the way down?